I'd like to review textural and compositional differences that we see in volcanic rocks. And this should all be review based on what you learned in your Introduction to Geology course or the lab or your physical geology class with David Mustard. So if we look at just a set of typical igneous rocks, and igneous rocks being any rock that formed from molten rock at some point, we have two different kinds. We've got plutonic igneous rocks and volcanic igneous rocks. The plutonic rocks are those that crystallize slowly, cooled and crystallized slowly underground. And so the crystals had time to grow relatively large, and so you can see the actual individual crystals. There are dark crystals and light crystals and grayish crystals and tannish crystals. And then that's in comparison to volcanic rocks where the molten rock or lava crystallized above the surface, so it was extruded onto Earth's surface, cooled relatively quickly, and the crystals are small enough that you can't see them with a naked eye. It really requires a microscope to see the crystals. So those are the textural differences between plutonic and volcanic rocks. We also have glassy volcanic rocks like obsidian, where they cool, the molten rock cooled so quickly that no crystals formed at all. It's just a glass matrix. So it's not crystalline material, and that's obsidian. We also have compositional differences, and that refers to the chemistry of the rocks. And it varies from these lighter colored rocks up here at the top that look like granite, that we call felsic rocks, and darker colored rocks that we call mafic. They have more iron and magnesium in them, more dark colored minerals in them. So that's broadly how we classify igneous rocks. And let's show you a little bit more. If we just look at texture alone, you'll see that we have phaneritic textures in the plutonic rocks. So these plutonic rocks here have a phaneritic texture that refers to the coarse crystal size, so large crystal size you can see with your naked eye, and we give that texture the name phaneritic. We also have aphanitic texture, which is a textural term that's used for volcanic rocks, and that refers to a very fine grain size. And then, of course, I mentioned already a glassy texture, which is in volcanic materials that haven't crystallized any minerals. It is just glass, and that's obsidian or pumice. Look again at chemical compositional differences, and I've already mentioned the difference between felsic and mafic rocks. With felsic, that term referring to, let's dot there, the fel part of that word is for feldspar, and the sic part of that word is for silica, which is silicon and oxygen. So felsic rocks have more silicon, and the feldspars contain potassium, sodium, aluminum. That's what a felsic composition is. And that refers to both the volcanic and the plutonic equivalents, so the granite and the rhyolite. That's the granite. Not writing so well. The granite, and that's the rhyolite. Those are chemical equivalents. The only difference between the two is the crystal size. Now we also have mafic rocks, those darker colored igneous rocks, and that word mafic, we can break it down, refers to the magnesium-rich rocks. So the ma part is for magnesium. The thick part of the word is for iron. So they're more magnesium and iron rich. The word doesn't actually reflect calcium, but they're also more calcium rich, and they have a lot less silica. So more iron and magnesium rich rocks like basalt, the volcanic, mafic volcanic rock, so basalt, and the plutonic equivalent, which is a gabbro. Again, texturally different, chemically similar. We can put some volcanic and plutonic rock names to those rocks. And I've already mentioned rhyolite and granite as being the felsic compositional equivalents with the granite, the plutonic granite, and the volcanic rhyolite. Obsidian is actually the same composition. Obsidian is always rhyolitic. So these three are all equivalent in terms of chemistry. The only difference is a phaneritic texture, an aphanitic texture, and a glassy texture on those rocks. So the texture then results from how the molten rock was in place, or where the molten rock was when it cooled and crystallized. Was it above ground with the two volcanic felsic rocks we've got, or was it below ground with the plutonic granite? We also have basalt that I'm sure you're familiar with. That's the mafic volcanic rock. Its mafic plutonic equivalent is a gabbro. It's hard to see that there are visible crystals in that gabbro in this image, but they are visible in hand sample and clearly different from the basalt. And then we've got rocks that are sort of in between. Those are intermediate. Nothing fancy about intermediate. So the intermediate composition refers to something that's in between felsic and mafic. And typical igneous rock names for those are an andesite, or a dacite, or a quartz monzonite, or a granodiorite. Those are typical intermediate compositions. So to get a little bit more specific about the compositional differences in igneous rocks, I've talked about felsic, intermediate, mafic igneous rocks. I haven't brought up ultramafic yet, in part because this is a volcanology class, and the only ultramafic volcanic rocks are komatiites. It's an ancient rock. Komatiite. There are no modern equivalents, so there are no ultramafic lavas erupting or being in place beneath a mountain belt. So those are left over from an earlier part of the history of Earth. Now, as for the felsic intermediate mafic rocks that you'll see in class and in the field, felsic refers, again, to feldspar and silica, but specifically has somewhere between 55 and 70% silica. And that doesn't mean quartz. That means all the silicon and oxygen within the rock. And that includes the silicate part of the formula of all the minerals that are in there, whether it's biotite, muscovite, hornblende, quartz, or K-spar, or plagioclase like anorthite or albite. They all are silicate minerals. They all have silica in them. So those are relatively rich in silica, and they're dominated by the potassium feldspars. Those are also called alkali feldspars. Those include things like albite or Amazonite, that's a specific type of, I'm blanking on the mineral name. We'll come back to that. You're going to see plenty of K feldspars in the class, but those are the minerals that dominate in the feldspars that are present in the rock. So more than a third of all the feldspars that are there. We'll jump over to the mafic rocks next, just as a comparison. So again, that's the mafic end member for these compositions. 45 to 50% silica, and they're dominated by plagioclase feldspars. So anorthite, albite. Albite's a bit of a complicated mineral. I'll explain. It's a name for a sodium-rich plagioclase as well as an alkali feldspar. But in this case, the plagioclases that are there are dominated by calcium-rich end members, so that's the anorthite end member. So in addition to that, so there's less silica, they have more calcium, and they have these dark silicate minerals, and that results from the magnesium and the iron that's present. Now the intermediate rocks are somewhere in between, so 55 to 65% silica. Plagioclases make up more than 2/3 of the feldspars that are present, but there's still some of the alkali feldspars there. So that generally gives you an idea about the compositions there. We talked about the textures, so phaneritic, aphanitic being the coarse crystals in a plutonic rock versus a finer texture in volcanic rocks that you see that have an aphanitic texture. Porphyritic is a combination of the two, kind of. It's a texture that you would use to describe a volcanic rock that has large crystals within it that are visible to the naked eye. And what's happened is those large crystals that are called phenocrysts are crystals that formed early in a magma chamber in that molten rock, in that magma chamber, before it got erupted as part of, when it was extruded onto Earth's surface. So those are early formed, but it has this different texture that we call porphyritic to describe the two different grain sizes. So the ground mass, or the body of the rock, most of the rock, is this fine grained texture. You could say that the ground mass has an aphanitic texture to it. Here's a porphyritic texture that you would see in hand sample here. So in a hand sample, you see these large crystals of what's probably hornblende. It might be a pyroxene like augite, but they're large crystals in this fine-grained matrix that you can't really identify any specific crystals. If you were to look in a thin section of the rock, so this is a very thin slice of rock that you put on a glass slide, stick under a petrographic microscope that uses polarized light, and you'll see that those large crystals might look like this. You see the large crystals standing out that are easy to see, and they're in this fine-grained matrix, somewhere in here, that you can't really see anything. There aren't any large crystals. It's very fine-grained. That's a porphyritic texture. The other terms that you might end up using are glassy, and you would refer to a matrix glassy like the obsidian that I showed you. That's a glassy texture. We also see pumice, which is also volcanic glass, but it has a lot of vesicles. So it has a lot of bubbles, basically, that were gases that were trapped in the rock as it cooled and solidified. And we give rocks, and it might not be glassy texture, any volcanic rock that has those bubbles preserved, or those little holes or pores preserved, we call that a vesicular texture. We won't see these in the first lab in class, but pyroclastic rocks, or pyroclastic material, or pyroclastic ejecta. That's a material, we'll use ejecta here. That's a material that gets erupted out of a volcano and either erupted somewhat violently as large particles or semi-molten blobs of volcanic rock, those might end up being aggregated into a rock, a pyroclastic rock, and those would be given a texture called fragmental. But we'll address that later on. Okay, here are a couple of glassy volcanic rocks. I've mentioned obsidian, I've mentioned pumice, and they are compositionally the same, texturally a little bit different. They're compositionally the same because they're both rhyolite in composition, so they're felsic. They're both glassy, but the pumice has it's a frothy glass. It has a lot of vesicles preserved in it. Okay, so as far as classifying these rocks and how we're going to end up naming volcanic rocks, and you're going to see some plutonic rocks in this class and on the field trip too. But I've given you a set of compositional terms, and I've given you a set of rock names that span that range of composition for volcanic rocks, as well as for plutonic equivalents. But volcanic rocks are particularly tricky to name because they can be so fine-grained. And so another thing that you're going to use to classify volcanic rocks is what's called the color index. And that's simply the percentage of dark minerals that are in the rock. So either if it's a fine-grained basalt that's very dark gray or black, you can't see the crystals, but you can tell that it has a high percentage of dark minerals. And you might even say it's 50% dark minerals if it was dark gray. If it's a let's say if it's a porphyritic andesite, so it has a gray matrix but white phenocrysts in it, you might decide that it has a smaller percentage of dark minerals in it and give it a lower number for a color index. So this is kind of relative. You're not going to be able to establish a firm percentage of dark minerals in these rocks, but keep in mind that you're going from lighter colored rocks to darker colored rocks, and that you're going to use the color, even though it's not terribly reliable, to name these rocks and to estimate their composition. Now, there is a standard way of classifying volcanic rocks that's based on how much quartz, that's the Q, what percentage of alkali feldspars or what percentage of plagioclase is in the rocks, that's the QAP. But as I said, we can't really estimate reliably just what percentage of those minerals would be in a rock. So we, for the most part, can't use that very easily. So we come back to the color index. Really, when it comes down to it, when you need to name a volcanic rock, you have to crush up the rock, analyze it with an X-ray fluorescence machine or XRF, and that gives you the composition. It gives you how much silica, how much potassium, sodium, all the elements that you would expect to find in igneous rocks. And we end up using the alkali elements, so the sodium and potassium, versus the amount of silica in the rock to actually name the rocks. So a basalt falls in this field with around 45 to 50% silica and a very low percentage of the alkali elements. Whereas we can use, let's use a rhyolite up here. So much higher percentage of silica, so 70% or more silica, and quite high percentage of the alkali elements. So that's really what you would do if you needed to name these rocks accurately. Now we've got, you're going to see in your first lab volcanic rocks that are a result of lava flows. So these are not just basalts, but you're going to see a textural and compositional range of rocks that resulted from these flows. And I'll have you look down a microscope and prove to yourself that the textures that you can see in the thin section of the rock really do reflect what you see in a hand specimen of the rocks. And you're going to use both the color index, so how dark the rock is or how many dark minerals you can see in the rock, as well as what the composition of the phenocrysts is. Are they dark colored phenocrysts, or do you have light colored or white phenocrysts? Do you have quartz phenocrysts in there? You're not going to learn how to identify the minerals in thin section in this class. You'll do that in Mineralogy and Petrology 1. But for now, you're just going to use what you know about mineral identification in a small set of minerals that you've covered in Intro Geology, and the color index to try to name volcanic rocks.